Today's tutorial is going to be about how to implement collimator sights or reflex sights properly, in particular for virtual reality. And the reason that reflex sights are really interesting for VR is really for the same reasons they're interesting for military purposes. They're easy to use. And so when you're making arcade games, when you're making location-based VR content, well, it turns out that the red dot slash the reflex sight slash the collimator happens to be a really cool way for people to aim at things and to get a really good overall experience. The problem is I've experienced a lot of games not quite implementing reflex sights the way that they should be. I've seen some really terrible implementations. I've also seen some okay implementations, but unfortunately I haven't really found any real resources as to how you should go about implementing a good reflex sight. So let's just start with a little bit of theory really quick. Essentially, so what makes a reflex sight so special? Well, it's the fact that there's parallax correction. So you actually don't have to look down the sights of the guns in a perfectly straight line in order to be able to use those sights. And that's what makes them easy to use. You don't have to have perfect posture. You don't have to have your cheek up against the stock in order to be able to use them. And that, of course, is also another big problem when it comes to VR. You have a headset in the way, and that headset has a tendency of colliding with physical accessories. So essentially we have here a picture or an animation or a GIF of what a reflex sight looks like in practice. So essentially as you move your head left and right, so the actual rifle here is not moving, and of course the target in this context is quote unquote not moving either, but as you're moving your head left to right behind the sight, the actual reticle stays perfectly aligned with the target. And sights aren't the only application that we could be looking at here. We have another example here on Wikipedia where we have aircraft HUDs as well, which actually also use the same principle, the exact same principle, to project images into the user's field of view. So what we're going to be going over today could also apply in that context as well. So I don't want to get into too much theory as to how they're built physically, because that's not really relevant in this case. But essentially what it comes down to is we have a reticle, and that reticle has to be parallax corrected so that the head's perspective, the camera's perspective, doesn't actually influence where the gun is shown or the weapon is shown to be pointing. Alright, so that's essentially that. So yeah. So before we begin, there's a few things that I'm going to be using. You're free to use these specific things or anything other that's equivalent. So the first thing I downloaded here was the collimator site. Here it's a free model that you'll be able to find on TurboSquid if you type in reflex sight. So I invite you to download that. And I've also brought a couple of modifications to it. So the first modifications that I brought to it is to bring the actual lens down to 0,0, which is going to be rather practical. Later on, just avoids having some offsets and having to deal with some stuff. You don't actually have to do this. If you understand how the shader is written, you could rewrite it to compensate or whatnot, but to keep things simple, I don't really want to get into those details right now. So I've brought the sight down to 0,0, the center of the lens is at 0,0, and the other thing that I've done as well is I've essentially taken the lens part, let's actually unselect that. I've taken the lens part and I've assigned it to a new material. So that way we are going to have the lens body and then, the collimator body, and then we're going to have the collimator lens as well that we're going to be able to use. So those are essentially the modifications that I did, and I exported those into Unity. Keep in mind, I don't want to go over export options in this particular tutorial, but you'll want to make sure that you export them. If you want to be able to follow things exactly the way that I'm going to be going over them, you want to make sure that when you export things that you really have no rotation or scale induced by the fact that Blender is a Z up coordinate system, right-handed Z up coordinate system, and the fact that Unity is a left-handed Y up coordinate system, which does have a tendency of doing some weird stuff over here. So just make sure that when you export, and maybe I'll do a tutorial on this eventually, but other people have already done this as well. Just make sure that you have 0, 0, 0 in your rotation and 1, 1, 1 in your scale when you actually bring it in. So that way you're going to have the same coordinate system as I do. Of course, it works even if that's not the case, but you'll have to be adapting your code or your shader accordingly, because the orientation of the object itself, we want the site to parallax correct according to the z-axis in this case. But if you happen to be along the x-axis or be along the y-axis because the whole thing's rotated, well, it's going to work, but you're going to have to code things slightly differently than what I will be doing. Okay, the other thing as well that I've prepared before going over this is a very simple image. Here I put this together in Inkscape. This is going to be our reticle. This is just a black and white image. There's no alpha, where essentially white is where I want the reticle to be and black is where I want transparency to be once we've got it into the Reflex site. Okay, so let's get right into it. So the first thing that we're going to be doing is essentially creating a body material. This is optional, you can do this or not. I'm not going to bother importing the textures of the original site, but you can feel free to do that if you'd like. So essentially we're just going to assign a new material over here very simply, and we're going to make it black, adjust the smoothness a little bit. Yeah, I mean, it doesn't really matter, but just for the sake of completeness, let's do that. And the other thing that we're also going to be doing is we are going to be creating a new material, and this is actually going to be the lens itself. And so in this case, we can assign it, we can make it green just to make it stand out, or whatever color we want. So here we are, now we have our site with two different materials, and ready to receive our shader. So we're going to go ahead and create a new shader, and this is going to be a very simple unlit shader. So this is going to be the site lens. Alright, and what we're going to do is we are going to call this, we're going to put this in the group, let's just put it in the group custom, and we have site lens. So there we go. And what we're going to do right away is go to our site lens body, we are going to go custom and site lens, there we go. Let's open up that shader. Let's open up that shader and let's start working on it. The first thing that we're going to want to do is to make this shader transparent. So right from the start, we're going to change this for transparent, and we are going to set the Q. By default, it's going to be rendered along with the opaque geometry, but we want to render it with the transparent geometry after the opaque geometry has been rendered. We are going to be turning the Z test off, and the other thing that we're going to be doing is essentially setting our blend modes such that we multiply our color by alpha, and we essentially take the whatever it is that we're writing over, and we're going 1 minus source alpha and multiplying it by that. So that's essentially, this is standard blend mode. This is pretty much just the way you think alpha should be behaving. And then what we're going to do, just for the sake of testing it, is instead of returning color in the default shader, we're going to go down to the bottom of the shader, and we are going to replace this with a fixed for of 0, 0, 0, and let's just do something that's semi-transparent. So that way, normally, if everything went well, which it may not, but it did, okay, good, we end up with a semi-transparent lens. Great. So there's no reflections to this. There's no, I mean, this is like a really basic shader. We're not going to go into, you know, getting the reflection and stuff like that out of the lens. You can essentially adapt everything that I'm going to be showing right now. I'm really going to be focusing on parallax correction inside of the lens itself. Okay, so that's great. We're off to a good start. We now have a lens, and the next thing that we're going to be doing is we are going to make our texture appear on that lens. So we're going to take our site lens, we are going to give it the texture that we want, and I didn't bother mapping the UV map properly in this case, and I would actually recommend not doing that, because we would rather base our UV map not on an actual UV map, but rather on geometry. So we're actually going to we're going to generate that UV map manually inside of the vertex shader. So to do that, we're going to essentially remove this line over here, and we are going to make the UV equal to the vertex positions x and y. So essentially it's just going to be v.vertex, and we want to just keep the x and y coordinate, and that's going to essentially now generate us a UV map based off of that. So normally we should, if everything goes well, it doesn't always go well, we should have that UV appear, or have our site normally should have appeared over here, but of course it doesn't, because, and okay, right, so the reason that's not working is because the coordinates are centered around 0, but a UV map goes from 0 to 1, so we need to throw in an addition of 0.5, 0.5. So there we go. Oops, still not. Float to 0.5, 0.5, and there we go. Now we have our dot appearing. Now we also want to scale, so we can throw in a scale factor in there. Let's say divide by 0.25. So it's a scale factor. We're dividing, the smaller the number is to make it smaller. So there we go. Now we end up with our site appearing on there. Now we have another problem, and that problem is the fact that our texture is repeating along our surface, because our UV maps go beyond the reticle. And we're going to have to solve that. We're going to have to change that for sure, but we're going to actually take care of that a little bit later. So first thing we're going to do is we are going to use that mask in order to modulate the alpha of our color. So first thing we're going to do is we're going to create a new parameter over here, which is going to be color. That's going to allow us to define the color of our red dot. So by default, we're going to make it red. Of course, it can be any color that one might desire. And while we're up here, we're going to create a few other variables as well, parameters, and we are going to create one called distance, which is going to be a float value, which is going to have a value of 100, arbitrarily set for now, and a value of scale, which by default we are going to be setting to a value of 1, because everyone loves a scale of 1. Okay, so we need to redeclare those down here. So we've got distance, we have scale, and finally we have color, right? Which is going to be a float 4. Voila. Okay, so now what we can do is, instead of reading the texture for the sake of reading, well, actually, let's call fixed 4, let's go read the texture. Let's just call it text in this case. Next, we're going to have fixed 4, in this case is going to be col, which is going to be, in this case, color. Next, we are going to be going we're going to take the alpha and we're going to map it to text.r. So in this case, we could be using the luminance instead or something along those lines, but there's really no point in calculating that. So we're just going to use the red channel and essentially discard the data that's in the green or the blue channel. In theory, if you're trying to do some really cool stuff, you can use the other channels for other stuff and be efficient. But in this case, I decided to not be efficient. So we've got our color, and what we're going to do right away, actually, let's start with that. And what we should normally have at this point, if everything goes well, let's keep our fingers crossed, is, there we go. Now we have our color that just came out, and we can set it to pretty much any color we want. And so let's actually set it to, yeah, let's leave it at green. Okay, so there we go. So now we have a site, well, not really actually, but now we have a site that's being rendered. It's essentially being rendered off of on top of everything because the Z test is set to off, and yeah, essentially that's where we're at this point. Okay, now as I mentioned earlier, we also want to stop our texture from repeating. So to do that, it's really simple. If u or v is greater than 1, then we're going to set the alpha to 0. If u and v is greater, u or v is greater, or sorry, less than 0, then we're going to be setting the alpha to 0 as well. So that's pretty much all that it comes down to. So we're going to go i.uv.u is smaller than 0, or i.uv.u is greater than 1, or i.uv.v is smaller than 0, or i.uv.v v is greater than 1 if we meet this condition, col.a is equal to 0. So essentially we're just overriding the alpha if ever we don't meet those conditions. And of course we have an error. What might it be? Just get the shader to recompile here. Whoops. U line 65 uv.u. Right. Of course, we're not talking about uv in this case. We are talking about x and y in this case. So I apologize. I.uv.x, I.uv.x, I.uv.y is smaller than 0, I.uv.y is greater than 1. And there we go. Now we end up getting rid of that repetition. So we're getting somewhere. We've got a site, but of course, this is in no way whatsoever an actual reticle or an actual site because, well, if we're trying to aim at an object downstream, so let's actually just drop a cube here, which we're going to be using later. So let's just set its coordinates to 0, 0, 0, and let's just drop it 100 meters downrange. Now, what I would expect, the site right now is pointing perfectly at it, but what I want is that no matter where I'm looking at it from, if I'm moving my head or moving the camera, I would expect that reticle to stick to it, which of course is not the case. So I've actually seen some VR implementations done exactly like this, which is awful, because for all intents and purposes, you're playing without a sight, which just baffles me. But that being said, so essentially, we're getting somewhere, but we're nowhere near actually having the site that we want and need in this case. Okay, but we do have the beginnings of the shader that we want. So before we get into actual parallax correction, let's actually implement the exact effect that we want. So one thing that we could do is actually just take the vertices that we have here, and we could also push them down range. So if we actually just add in a float 3 over here, and on that float 3 we give it coordinates of 0, 0, 2, for example, so pushing the site 2 meters downrange, well, now we actually start getting some of that parallax effect that we actually want, and we're actually getting some of that correction. And in fact, that's already a good start, if you will. We could actually throw in a scale factor over here of 2 as well, just to bring things up. So we could actually throw this downrange at 100 meters, and we could also increase its scale to something that's not going to be too far out of our way, and now we actually end up getting that parallax correction, and that's actually exactly the result that we want, because for all intents and purposes, the vertices for that site are now exactly aligned with that cube, and no matter where I look at it from, well, that's going to be the case. But of course, I mean, it doesn't really make any sense, because quite literally my vertices are in this or on this cube, right? So, well, now we're clipped out of the camera, so we're not seeing it. There we go. So now if we don't have it clipped out, so we've got the site over there, really far uprange, and essentially now we have our site there, and it's literally being rendered on the cube. Now, of course, this doesn't really make any sense, and this doesn't make any sense, or this implementation wouldn't make any sense for a few reasons. And one of those reasons is, well, if I'm not looking in my site, well, that site is still there, which doesn't really make any sense. If you're trying to make an arcade thing or something like that, yeah, that could potentially work. If we're trying to stay a little bit realistic and actually have people, aim down the sites, at least up to a certain extent, well, obviously this is not an adequate implementation. There is a very easy way of fixing this, and this was actually the way I first implemented a reflex site or a collimator site, is to use shader stencils, which can be used in order to essentially generate a lens up in the actual site. You render a crosshair or a reticle downrange, and then what you do is you use the lens to clip out or to allow the reticle to be rendered. So I'm not going through the details in this tutorial in particular, but if you're familiar with shaders, if you know stencils, then you would probably recognize that we could actually get the exact effect that we want using stencils. Okay, so if we keep going, this is essentially the effect that we want, but we just want the crosshair to be rendered only if it's in the lens, and we don't want it to be rendered at all if we're outside of it, like here. So we don't want to see this. Okay, so in order to do this, we are going to be undoing what we just did. And conceptually, all we're going to be doing is, based on the camera's position, we are going to be moving the UV map of the lens such that it compensates for parallax. So essentially, it's very similar in a very calculated way to website scrolling parallax backgrounds in a way. So how exactly are we going to do that? So essentially what we have right now is we have a camera. That camera, if we're in view space, is located at coordinate 0, 0. And it's looking at a lens. The lens is mounted on top of a weapon of some sort, and it is located in view space in front of the camera somewhere. Could theoretically also be off screen, doesn't really matter, but for this particular instance that we're looking at, it's located somewhere in front of the camera, somewhere on the screen. So just a quick note, everything in this diagram is 2D, but of course it's implied that everything here is 3D. It's just much easier to draw and understand and look at in 2D rather than 3D, but we are talking about 3D space here still. So we're looking at this from the top, just for the sake of clarification. So we have a camera. The camera is located at 0, 0. Then we have a lens. The lens is located somewhere in front of the camera. And then we have our projection plane. And this is essentially where we want the reticle to appear, or where we want the reticle to look like it appears from. And so it's bigger, it's been scaled up, and it's further back. So it's maybe 100 to 1,000 meters behind the lens. So D here is equal to some number in the range of 100 to 1,000. It actually doesn't really matter. It's pretty arbitrary at the end of the day. And we have this plane over here. And what we want to do is we want to take vertex V over here. So this is just the vertex that we're examining in this case. And we want to project it onto this projection plane. And we want to figure out what its UV coordinate is. So in this case, we have V here. V lines up with the camera. For all intents and purposes, we want its UV coordinate to be equal to, well, Q here has a UV value or a U value because we're looking at it from the top. We don't know we don't have any information about V in this view. So U here is equal to 0. For point R here, U is equal to 1. And for V prime, which is essentially V here projected back, becoming a V prime intersecting with this plane, so V prime, for all intents and purposes, in this case, intuitively, we can kind of look at it and go, well, you know, the U coordinate of V prime is probably worth something along the lines of 0.92 or something like that. So if we bring that back to V over here and we give V a U value for its UV map of 0.92, well, it will, if for all intents and purposes, and if we do this for all 4 or all n vertices of our lens, in this case we have a lens that's described along a curve. If we do that for all of the vertices that are there, well, now all of a sudden what we'll end up doing is we'll be displaying the texture that would normally be displayed here. And for all intents and purposes, the camera, even though we're rendering it here, the camera will believe, quote unquote, it will create the optical illusion that it's actually being rendered behind the camera from a perspective point of view. To be able to solve this, we have a number of little equations that we have to go through. It's nothing particularly complicated. It's some pretty straightforward vectorial algebra. So the first thing that we're going to do is we're going to start with this equation, and this is the equation that defines our plane. So our plane is defined by two things. It's defined by P0, which is over here, and defined by N, which is over here. So N is the normal, and P0 is one of the points on the plane, and in this case we're going to be more accurate than that. We're going to say that it's the center point of our reticle, the exact center point of our reticle. So there we go. So now we have P0 and we have N, and essentially the way we describe our plane is any vector or any point that's subtracted from P0, so that's essentially the vector that would be generated between the point and P0. If it's perpendicular to our normal, so the dot product equals 0, well then it's on the plane. And yeah, that makes sense. That would be the description or the way we would define a plane in this case. So even in 2D this works. Our plane happens to be a line, but of course in 3D that plane can come out of the page as well. The next thing that we need to define is the line, and that's going to be the line over here, and the line can be defined as any point P, which is proportional to V. So because our camera here is at point 0, 0, and we have vertex V here, or coordinates V here, if we multiply those by a scalar, A, we can essentially describe every single point that goes along this line. If a is smaller than 1, then we end up being on this segment. If a was to be negative, we would be on the segment that would be behind the camera, which we don't care much about. And if a were to be greater than 1, then we would be on the segment that links v to v prime and continues on forever and ever and ever. So what we're trying to do for all intents and purposes is we're solving for a. That's what we want to do, so that we can figure out where v is by multiplying, where v prime is by multiplying v by a. So how do we do that? Well, we substitute. P here is going to be substituted by AV. So essentially we end up with this equation over here, where for all intents and purposes, well, what we're trying to resolve, the equation that we're trying to resolve is AV minus P0 dot product n is equal to 0. And that, for all intents and purposes, can only describe one point, and that's going to be the point V prime. So from there, simple inversion, A is equal to P0 dot n divided by V dot n. A few interesting things to note at this point. There are two interesting things to note. The first is to note that the direction of n will have no significance, which makes sense. It's what we would expect. If n is positive, well, it'll work. If n is negative, it will work as well, because the sign of n is going to be compensated for or cancelled out through this division. So n doesn't have to be this way, it can be this way as well. It really doesn't matter. And the second thing to note is that once we've found A, well, I guess it's our next step, that once we've found A, if we want to get V prime, all we have to do is multiply V by A, and all of a sudden we have V prime. So now we know the coordinates of this point in space for given an input value of V over here, which is essentially what our shader is going to do later on. It's going to be trying to, well, not trying, it's going to be computing the value of V prime. But once we've found V prime now is in 3D space. But what we want is a UV coordinate. We don't want the 3D view space coordinate. That's not what we're looking for. So how do we get that? Well, essentially, we are going to be using another vector. In this case, it's going to be vector Udyr, or the direction of U. And we can compute that essentially just based off geometry. In this case, it's a unit vector that is in the same direction as our line QR, which for all intents and purposes is simply perpendicular to our distance vector, if you will. So for all intents and purposes, if we want to know how much in the U direction we are, it's fairly straightforward. All we have to do is take our zero reference point, which in this case is actually going to be, there's a mistake here. Our zero reference point is P0. We're going to subtract V prime from V0, generating the vector between these two. We are going to dot product it with Udyr, and that's going to give us a multiple that describes how many Udyrs it takes to get to V prime in order to compose V prime in an orthogonal base, or orthonormal base, sorry. So essentially, once we've got that, now we know the U coordinate centered on 0, or centered on P0, that V prime should have. So if, for example, this vertex were to line up perfectly with P0, this value would actually be 0. If our vertex lines up perfectly with, well, a point that is 1 unit away from P0 along this line, then VU would be equal to 1, and conversely, if we were 1 unit behind P0, then this value would be -1. So now from that, we can throw in a scale factor, generate our UV map, and essentially offset it by 0.5, 0.5. We'll get around to that later, but of course this here is centered on P0, but at the end of the day, we'll want to center it on to a point which is actually to the left, so we get 0 on the left, we get 1 on the right. Okay, so enough math. Thanks for your patience about it, but let's get into how we actually code this in shaders. Okay, so we're going to push this down a little bit. So we now have our UV map over here. We generated our own UV map, but for all intents and purposes, this is no longer going to apply. So there's a few things that we need to do at this point. And that's going to be, in a lot of cases, just to generate the different coordinates that we have here. So we're going to start by generating our origin. Our origin, what I'm going to call the origin or the lens, actually let's call it lens, which is going to be this point over here, which I haven't actually described or haven't actually written out. But let's just make sure we have that defined. So that's going to be float 3 lens. Let's go all out, lens origin, and that's going to essentially be equal to unity object to clip, to view. So we're going to be doing everything in view space in this case. Unity object to view position, of course, is a unity function, and what we're going to be throwing in here is the 0, 0, 0 coordinate. So essentially what we're doing is we're using the unity object to view position to change the coordinate 0, 0, 0, which for all intents and purposes is the origin of our geometry, and we're essentially just figuring out where that geometry is once it's in our view space. So that's going to give us the origin. So for all intents and purposes, that would be the point here, but instead of looking at it in world space, which is what we have here, which is 0, 0, 0, now we're getting its coordinate in view space, and in this particular instance, well, it would be somewhere in the center with probably x and y very close to 0, and I don't know, maybe it's a few meters in front of the camera, so the z coordinate or the z output of this function would be a positive number of maybe 1, 2, 3, something along those lines. Anyways, so what we're doing here is we're just generating, we're not working in world space, we're working in view space, and view space is essentially the camera coordinate. So z is forward from the camera's perspective, and x is left, and y is up. Okay, so we're going to generate a few other elements as well. So we've got p0. Oops, let's get back to this. Okay, so now we've got p0, and we also want to have p0 in there, and p0 is we're going to be using the same trick. So some of you might be wondering why I'm not just decomposing the model view matrix. We could do that, it's just less intuitive. I'd rather not do that for the sake of this tutorial. It would probably be more efficient on some of these, but for all intents and purposes it doesn't really matter. In this context, we're not talking about a high vertex count, we're not talking about a high object count. This is a unique object. Usually there aren't a ton in the level, so anyways, there are optimizations that are possible, just mentioning that. Okay, so we've got p0, we've got our lens origin, we want to generate n. So as I mentioned earlier, n, it can pretty much come from anywhere, and it can pretty much be in any direction. So what I'm going to do is I'm going to subtract a distance of 1 from our lens origin. And there we go. That's going to give us n. So essentially that's taking this coordinate over here, somewhere in the whereabouts of 1 unit ahead, and subtracting it from the origin. That gives us a vector which happens to be in the opposite direction of the n that I have here, but it doesn't really matter, as I mentioned. We are going to generate Udyr, which is, for all intents and purposes, we're going to be doing something very similar to what we've done over here. So Udyr is 1, 0, 0, so we're just essentially pushing a vector over by 1 on the x-axis and then transforming it into view space and subtracting it from lens origin, which we'd already computed. And finally we have Udyr, which we're going to be doing the same trick. And voila. So now what we've got is a few of the constants that we need in here. Yeah, so that's essentially that part of it. And we're at the point now where we will be going down this formula and essentially implementing it. So the first line we actually need to implement is this one here. So float a is equal to, so float is a scalar, the dot product of, in this case, p0 and n. And we are going to be dividing that by the dot product of v. So for getting a line over here, so float 3 vert, and same thing. Essentially we want to know what the vertex position is in view space. And so the intersection will be, sorry, not the intersection, but the vertex is very simply located at, well, we take the vertex multiplied by the model view matrix, and we end up with its vertex position in view space. Since all of these are in view space, it's important that that ends up being respected. Okay, so V and finally N, which makes sense, cancels out the other end. Okay, so that's our A, and then the next part that we need is going to be our V prime, or let's just, for the sake of uniformity, let's call it vert prime. And so vert prime is going to be equal to A times vert. I hope there's no surprise there. So at this point, we've done a lot of math, but we haven't done anything with it. So now we need to generate our UV coordinates. So it's going to be very simple, very similar to what we've done before. So we're going to have O dot UV, which is going to be equal. So we're just going to start with the very direct. We're going to write this over a few different lines, just makes things a little bit easier. So O dot UV is going to be equal to vert prime. Right, so it's going to be equal to, in this case, we want our UV coordinates. So it's going to be a float 2, and that float 2 is going to have two parts, hence float 2. And the first part is going to be the dot product that's going to be between V prime minus P0. So vert prime minus P0. And as a second part, we are going to have Udyr. And then, oops, dot Udyr. Essentially, we're going to be replicating that again. So vert prime minus P0 a second time. And this time we're going to be doing the dot product. Same mistake twice. We're going to be doing the dot product with Udyr. So now we have our UV map. But the thing is, we want to scale this, so we're going to scale it. So we're going to go O.UV divided by, we're going to scale it by two things. We're going to scale it by the scale factor, and we're also going to scale it by distance, so that for all intents and purposes, when we play with the distance value, it won't actually make the reticle bigger or smaller. I'll just kind of normalize things, because as it gets further, we want it to get bigger. As it gets closer, we want it to get smaller, so that its actual size in our viewport or on the lens itself remains unchanged. And so as a last step, we are going to be, so at this point we have a UV map that's centered on 0, 0, which is not what we want. We want a UV map that's going to be centered on 0.5, 0.5, as is a classic UV map. And so we're just going to essentially add in 0.5, 0.5. Pretty straightforward for that last part, at least. Okay, dot. We have a mistake here. Line 60, so on line 60 dot P0n dot P0n V vert, of course. Right, so obviously a mistake, so here we should have vert, not V, as V is our input structure. Alright, and there we go. So now, if everything goes well, we now have a site. It's a bit big, but we have a site. And so if we take that, and we scale it down, maybe 0.25, maybe a little bit less, 0.12, there we go. So for all intents and purposes, now we have a site. So let's see if our math is correct and everything works out the way it should. It's looking good so far. But the real way to test is, well, if I put a cube in there, does that cube actually stay aligned with that site? And it does, which is a very, very good news. But another thing that we should also be testing is just make sure that if we take that site and we rotate it, that it continues to work as intended, which it does. Okay, so if you're following closely, you're probably going to have the following question, which is, well, we've set this distance to 100 meters, but well, that's kind of arbitrary, right? What if my target's at 1,000 meters, or what if my target's at 10 meters? Well, what happens with that? So in practice, reflex sights actually also have this problem, but it's not really a problem for all intents and purposes. The actual calibration point has to be defined. So you can actually, a lot of reflex sights are calibrated to infinity. So for all intents and purposes, we can't We might have been able to write a shader that does that instead. Maybe we'll do that another day. But if we set this to 1,000, for example, well, we're getting pretty close to infinity for all intents and purposes. And you'll actually notice that even between 1,000 and 100, there's really not a whole lot of a difference. It pretty much behaves almost exactly the same way. If I make that, even if I make it 10,000, it's going to be very similar. Of course, there's going to be a point where this is going to break down, I would expect. No? Wow. I would have expected it to break down at some point just because of floating point precision or something along those lines, but hey. So if we leave it at 1,000, that's great. Because for all intents and purposes, it pretty much works for anything. So if we bring this back, if we put this at 1,000, so already you see that the cube is at 100 and the crosshair is at 1,000, and well, those follow each other quite nicely. Where you're going to see a big difference is if we could, step out of this quite far, but of course that's never going to be the case. Okay, so let's keep going. If we take this and put it at 1,000, of course it's going to work perfectly because now they perfectly match. So we see that those handles are exactly at the center of that site, even though we don't see the cube anymore. And even at 10, here you're actually going to notice there is a difference if you really pay attention to it. But the thing is, at 10 meters, your targets are usually so big that you don't really need that much accuracy when it comes to your site. And provided that you're relatively centered, well, you maintain accuracy. So essentially for all intents and purposes, we set the distance to an arbitrary number, just set it to 1,000, that essentially works. And that's that. So there we go. So that's essentially how you make a collimator site, a reflex site that actually does adequate parallax correction and makes sure that, well, whatever your weapon is pointing at, your sight is also pointing at when you're looking down it. So as I mentioned earlier, there's a few other applications for this as well, namely Huds, cockpits. You can use this if you want to have a car dashboard that projects a map or something along those lines. The same tricks can be used. Of course, this doesn't really make all that much sense for anything other than VR, where the camera perspective and the object perspective can be drastically different and in the user's complete control. Alright, so there you have it. We have a sight that corrects for parallax. It behaves the same way a red dot does in reality. So someone who actually has had one of these in their hands and tries your VR game, if you implement it this way, will immediately recognize it and be familiar with it. And even for new users, the quote-unquote noobs, this is much easier to use than pretty much everything else out there, except maybe like a laser sight or something where you just kind of have like an arcade laser pointing wherever it is that you want to shoot, which works for some content but doesn't necessarily work for others. So from my experience, this is pretty much the easiest thing to use. It works well. It's super intuitive and people just kind of get it right away. Look down the sight, put the red dot or the green dot or the blue dot, depending on the color that you decide to use, on your target and squeeze the trigger. So anyways, I hope you enjoyed, and I hope you'll be joining me for future tutorials, and thank you very much for your time.